When we discussed Boyle's law, we plotted a graph of P versus V. And the graph was something like this. For the theoretical values, which were obtained by the formula PV is equal to constant, we got a graph like this, a straight line graph. Whereas the ideal values, when the values were actually measured experimentally, the graph was something like this. And based on that, we concluded that at lower pressures, at low pressure, the gases behave based on the gas laws, meaning they obey gas laws, right, more closely. And therefore we can imagine infinitely small pressure, infinitely small or low pressure. And at this very low pressure, what will happen is, or what will probably happen is that this particular line, dotted line, will nearly match this particular line. And therefore we can say that the gas will obey gas equations like Boyle's law, Charles' law, and law of pressure. And such a gas, which is at infinitely small pressure and which obeys gas laws, is known as an ideal gas or perfect gas. There are a few characteristics of this imagined theoretical ideal gas, right? One is that it obeys gas laws. Two, particles or molecules are infinitely small and no force of attraction or repulsion between the molecules. So these are the three properties of this theoretical imagined ideal gas. Right? It obeys gas laws, as we discussed. Molecules are infinitely small; they don't have any mass. Right? Secondly, there's no force of attraction or repulsion between the molecules. The reason is that why we assume this is because since there is force of attraction and repulsion between the molecules, they do not obey gas laws. This is the reason, because whenever we are heating the particular gas or whenever we are giving energy, the energy being given is not just used for expansion or increasing temperature. It is being used to overcome these forces of attraction. So some amount of energy is lost in that, and therefore they do not obey the theoretical values of the gas laws. And therefore we make this assumption that, or this theoretical construct of an ideal gas, we assume that there is no force of attraction or repulsion. What this will also mean is that it will not be possible to convert this gas into a liquid or a solid, because if it's going to be a liquid, there will be force of attraction between the molecules, and if it is going to become solid, the force of attraction will become more. Therefore, when we make this assumption, we imply that this will remain in state of gas, irrespective of the low pressure or high temperature or low temperature. Okay, so this is the concept of an ideal gas, and we will be using this concept throughout our discussions on thermodynamics. Let us try to come to the equation of state of an ideal gas based on this theory. So let us assume that we have an ideal gas and the initial states are P1, V1 and T1. Let us say initially it is at P1, V1, T1 temperature, and finally it reaches temperature, let us say P2, V2 and T2. And let us say this process from here to here happens, right? This is the initial state, this is the final state. From here to here it moves through two stages. In the first stage, at constant temperature T1. Temperature this T1 is maintained constant, and pressure P1 is brought to P2 and V1 is brought to V dash. And in the second stage, P2 is already reached this value, so we'll keep pressure constant at constant pressure P2. Temperature T1 is constant over here, so that is brought to T2, and volume V dash is brought to V2. So we get P2, V2 finally. That's how we reach this particular state. If I focus on this particular part at constant temperature, so I can use Boyle's law over here because the process is happening at constant temperature. So P1, V1 is equal to P2, V dash. Initial state and final state for this particular part P. Therefore, V dash is equal to P1, V1 upon P2. Here at constant pressure, I can use Charles' law. In Charles' law, what we say is that V upon T is constant, so I can write V dash upon T1 is equal to V2 upon T2. Therefore, I can write down V dash is equal to T1 V2 upon T2. So I have got two equations for V dash. I can equate them. Therefore, I will get the equation P1 V1 upon P2 is equal to T1 V2 upon T2. I take P2 over here and T1 over here, so I'll get P1 V1 upon T1 is equal to P2 V2 upon T2. Therefore, PV upon T is equal to constant, and let us say this constant is called R. This R is universal gas constant for 1 mole of gas. So this is a constant, and therefore this equation takes the form PV is equal to RT, where R is a universal gas constant. If we take 1 mole of any gas, R will have a constant value, PV is equal to RT. Therefore the name universal gas constant. So this equation is for 1 mole of a gas. Now let us say we have been given the gas in terms of mass. Let us say we have 1 gram of a gas whose molecular weight is say capital M. Then how will this equation change? So PV is equal to RT. This is for 1 mole of gas. Now I have been given 1 gram of gas whose molecular weight is M. So I need to get this particular gas in terms of its molecular weight, in terms of its number of moles. Now if you have got M gram of the gas equal to molecular weight, the number of moles will be 1, right? Because molecular weight is the mass of 1 mole of gas. But in this case we have been given 1 gram. So what will be the number of moles? The number of moles will be equal to 1 upon M. And therefore this equation is for 1 mole. So for 1 upon M moles, I'll get the equation PV is equal to R upon M into T. And this term R upon M is denoted by small r, another constant R. And this is a specific gas constant. Specific gas constant because here we get the molecular weight. So it's molecular weight. That means this value will keep on changing depending upon the molecular weight. And therefore specific gas constant, whereas this is universal gas constant, whereas this is a specific gas constant. The value depends upon, or this value will keep on changing as the gases change, whereas here this will remain constant because it's constant of 1 mole of gas. So with this, we have had a look at the equation of state. The equation of state, as I said, is PV is equal to RT. Let me finish this video by writing PV is equal to RT. This is for 1 mole of gas, so for mu moles of gas, I'll get equation P is equal to mu RT. And this is known as the equation of state for an ideal gas or a perfect gas. We will be using this equation frequently as we study thermodynamics. In fact, nearly everything that we discuss in thermodynamics is based on this equation of state. In the next video, what we'll discuss is we'll look at R, capital R closely. We'll look at what are the units of R, what is the value of R. That is coming up in the next video. See you then. Thank you.